Let's continue discussing quadratic residues, and today's video is devoted to Legendre symbol. Sorry for my pronunciation, je ne parle pas français. Here is the definition of Legendre symbol. So let's suppose you're given an odd prime number p and take any integer a. So here's Legendre symbol. A bad boy Legendre decided to define the following notion. So you have a over p with brackets, and this produces you three outputs. It will return back 1 if this number a is a quadratic residue modulo p. This produces -1 if this a is quadratic non-residue modulo p, or 0, other special case, when a is divisible by p. This case is really special because it cannot answer any question about whether a is quadratic residue or non-residue, because it's a separate case. So to be more concise, Legendre symbol just answers the question whether a is going to be a quadratic residue modulo p. That's the main motivation. Here's the first example, which says that Legendre symbol of 2 modulo 7 is equal to 1. So it means that we have to answer the question whether 2 is a quadratic residue modulo 7. Now just recall the definition of a quadratic residue. It means that there is a solution to the following equation. So 2 is a quadratic residue modulo 7 if there is a solution for this congruence equation. And turns out there is indeed a solution. If you plug x equals 3, you get 3 squared, which is 9, but in the world of modulo 7, this is just exactly 2. So therefore, 2 is a quadratic residue modulo 7, and thus this Legendre symbol produces the output just 1. Another example of Legendre symbol is here. So Legendre symbol of 3 modulo 7 is equal to -1. So in fact, in order to answer the question, get this output, we have to answer the question whether 3 is a quadratic residue modulo 7. So whether there is a solution to the following equation: x squared is congruent to 3 modulo 7. And in fact, if you try to plug all possible x in the world of modulo 7, 1, 2, 3, 4, 5, 6, you will notice that this won't get number 3. So therefore, we cannot guarantee that 3 is a quadratic residue modulo 7, and turns out Legendre symbol must be equal to -1. And the final example here is this Legendre symbol 35 modulo 7, which is actually equal to 0, just because 35 is divisible by 7. And in fact, this scenario can be ignored throughout this section of number theory because it's rarely used. Most authors, they do ignore this third case. So you can define Legendre symbol in the following way, just producing 2 outputs. Whether it's 1, a is a quadratic residue, or -1 when a is quadratic non-residue otherwise. Now let's go back to the definition of Legendre symbol. So we care only about odd primes. But what if this prime is equal to 2? So this is the only even prime number possible here. Well, in fact, if we had defined Legendre symbol for this specific prime, then it will always produce 1, as long as you take a, which is not divisible by 2. So in fact, when p equals 2, so by modulo 2, you have all quadratic residues. So this is in fact the trivial case, which in my opinion can be ignored. And also we get rid of this case when p equals 2 just for the sake of some simplicity when trying to state something. And the next question is, why can't we just take any natural number we would like here? Well, in fact, this scenario can be possible if you try to define so-called Jacobi symbol. So it deals with those arbitrary natural numbers, and it has some motivation why we would like to compute them, but we don't actually need this symbol, so I'm gonna just skip this situation. Now the main goal here is maybe to learn how to compute Legendre symbol as quick as possible. Unfortunately, trying to compute Legendre symbol by definition is a bit weird waste of time. So therefore, we have to produce some results in order to maybe simplify the approach. And the first thing we would like to explore or investigate right now is so-called Euler's criterion, which says the following. If you have Legendre symbol A modulo P, then this object is going to be congruent to A raised to the power of P minus 1 over 2 and the whole thing modulo P. Now, if I mention Legendre symbol, I automatically mean that P must be an odd prime number. And in fact, right here, we do justify our choice because if P is odd, then this fraction is going to be an integer, so everything is fine. The main question left here is criterion of what? I will answer the question after the proof of this statement. Since Legendre symbol produces 3 outputs, so it depends on 3 cases, therefore this proof breaks down into 3 possibilities. The simplest case is when P divides A. So if P divides A, then by definition of this bad boy Legendre, this symbol is equal to 0 on the one hand. But on the other hand, if P divides A, then we have the following equation. So A is congruent to 0, and I should mention that this is modulo P. Therefore, if you raise both sides to the power of P minus 1 over 2, this is still going to be congruent to 0. But notice that 0 is just this Legendre symbol, so you can plug here, and you get the same equation modulo P as right here. The next case describes the following. When A is a quadratic residue modulo P. So it means that this bad boy Legendre symbol is equal to 1. But if A is a quadratic residue modulo P, then there is a solution to the following equation. And this solution is denoted by x0. And this x0 squared is going to be congruent to A modulo P. Now, if you raise both sides to the power of P minus 1 over 2, you get A raised to the power of P minus 1 over 2 on the right hand side, but on the left hand side you get x0 squared whole raised to the power of P minus 1 over 2, which is exactly x0 raised to the power of P minus 1. And then remember that this thing is actually congruent to 1 modulo P by Fermat's little theorem. Well, the one thing is we should check whether P does not divide x0. And in fact, it's true, since if P would have divided x0, then you would get in this equation that x0 squared would have been congruent to 0 modulo P, so A would have been congruent to 0 modulo P, which is impossible for our case. But look, A to the power of P minus 1 over 2 is congruent to 1, but this 1 is exactly Legendre symbol AP. So this symbol is congruent to A to the P minus 1 over 2 modulo P. The same equation as right here. The final case, and in my opinion the trickiest one, is when A is quadratic non-residue modulo P. So in other words, this Legendre symbol is equal to -1, and this is the last case we should consider. We're gonna begin with the following set. So I just decided to enumerate all elements, all non-congruent elements modulo P. 1, 2, 3, all the way up to P minus 1. Now let's take arbitrary element from the following set and denote this by y1. Then, if you consider this linear congruent equation, y1 times x congruent to A modulo P, then there is a solution to this equation. So you can solve this with respect to x and find the solution. Well, the reason is because GCD of y1 and p is in fact equal to 1, because this y1 is from 1 to p minus 1. Those elements are co-prime with this prime number p, so GCD is 1. And because GCD here is 1, so there is a solution here, and this solution is going to be unique one. This, in fact, unique solution we're going to denote by x1, and the crucial note here is that this element x1, which is from the same set, is not equal to y1. Because if they were equal, then we would get here y1 squared is congruent to a modulo p. But this means that a is a quadratic residue modulo p, which contradicts to our assumption in this case. Now let's continue almost the same process. We take the same set 1, 2, p minus 1, but this time we just throw out x1 and y1 from the set. We're gonna take an element from this set and denote this by y2. Now then, similarly, there is a solution to the following equation. y2 times x is congruent to a modulo p, for the same reason as before. And this unique, again, solution will be denoted by x2. Likewise here, x2 cannot be equal to y2 for the same reason as we did before with x1 is not equal to y1. But there's one more problem. The main question here is whether x2 belongs to the following set. Well, x2 is in fact a number from 1 to p minus 1. However, we need to make sure that this cannot be equal to neither x1 nor y1. Turns out this is true. So x2 cannot be neither x1 nor y1. That's because, for example, if x2 were equal to y1, then what we would have? We would have, first of all, this equation y1, so x2 instead of y1, times a solution here x1 is congruent to a modulo p. And also we have this equation y2 times its solution x2 is congruent to a. We have two different congruent equations where we have two solutions, x1 and y2. And this violates the uniqueness of the following equation if we would have solved with respect to y. So if we know that here is x2 and we would have solved with respect to y, then so this cannot be because it violates the uniqueness of the solution. So this is not the case. Likewise, if x2 would equal to x1, there would be also a violation to the uniqueness of the solution of linear congruent equation. So it's not possible. And then we go back to the following set 1 to p minus 1 and consider this, but now we throw not only x1, y1, but also x2, y2. Then from this set we take y3 and we keep repeating the same process. This is going to be a finite process because we have a finitely many elements, so we're gonna finish this process. So continuing this process, we will generate more equations. So we have already x1 times y1, which is congruent to a. Then we have x2 times y2, which is congruent to a. And we go further up until the last possible pair. X p minus 1/2, y p minus 1/2 is congruent to a. Those equations are with respect to modulo p. And notice x1, y1 different. We took them from the set 1, 2, p minus 1. Then we removed those elements x1, y1. And then we received x2, y2 different elements from this set. Then we threw x2, y2. And then we repeat the same process. So, in fact, turns out those elements, I mean x1, y1, x2, y2, up until the last x p minus 1 over 2, y p minus 1 over 2. This set is in fact the same as the set of numbers 1 to p minus 1, according to our algorithm. So those elements are just the same elements, but with the different order. So here can be maybe 3 or 5. There might be, for example, 2 and so on. So those sets are the same, but the order might be different. And now let's try to multiply all these equations and see what we get. So we have the following: x1 times y1, x2 times y2, and so on, up to xp minus 1 over 2, yp minus 1 over 2. And notice that each pair is congruent to a. So this is congruent to a, this is congruent to a, and this is congruent to a. Now, how many a's do we have? We have p minus 1 over 2. So the whole thing is just a raised to the power of p minus 1 over 2. And this holds in the world of modulo p. And that's on the one hand. On the other hand, if you rearrange these numbers in the natural order, you get in fact the following product. 1 times 2 times 3 all the way up to p minus 1, just according to the following result. This product is in fact just p minus 1 factorial, and we know something about factorial when p is odd, an odd prime number. This thing is congruent to -1 modulo p by Wilson's theorem. So totally we have -1 is congruent to a raised to the power of p minus 1 over 2 modulo p. However, this -1 from the beginning is in fact, is in fact a Legendre symbol, a modulo p. So I can just substitute this -1 to Legendre symbol of a mod p. And that's what I wanted to prove in Euler's criterion. And now I promise to answer the question why this statement is called criterion. So in fact, criterion of what? Criterion of whether A is quadratic residue modulo P. And this implies that A is going to be a quadratic residue modulo P if and only if A raised to the power of P minus 1 over 2 is congruent to 1 modulo P. So this if and only if defines a criterion what we needed. This specific result can be partially generalized. And now if you consider that A is a quadratic residue, but this time modulo n, where n is an arbitrary number bigger than 2, such that it is co-prime to A, so GCD is equal to 1, then it follows that A raised to the power of phi of n over 2 is congruent to 1 modulo n. The reverse direction does not hold if you take case when n equals 8 and a equals 3. You can check that this holds, so 3 raised to the power of phi of 8 over 2, so this is just 3 squared. In fact, this is 9, which is congruent to 1 modulo 8, so this holds. However, it does not imply that 3 is a quadratic residue modulo 8. In fact, 3 is not a quadratic residue modulo 8, and that's the exercise what you need to check. This result immediately applies from Euler's criterion. It says if you actually have a quadratic residue modulo P denoted by A, then the same A is in fact not a primitive root modulo P. Because first of all, by Euler's criterion, as mentioned above, we have the following. A raised to the power of p minus 1 over 2 is congruent to 1 modulo p. But suppose that A is actually a primitive root modulo p. A primitive root means that A raised to the power of Euler's Taschen function at point P, which is actually p minus 1, is in fact congruent to 1 modulo p. And furthermore, this would be the smallest possible power such that a to this power is congruent to 1. However, we found even smaller power where you raise a and you get 1 modulo p. So therefore, this is not the case. And that's how we can shortly prove this corollary. Now finally, we are ready to state some properties of Legendre symbol which can significantly simplify the calculation of Legendre symbol. Here's the first one. If you take two numbers a, b such that those are congruent modulo p, then Legendre symbol of a modulo p is equal to Legendre symbol of b modulo p. Again, notice that p has to be an odd prime number in order to define Legendre symbol. The second property is here. If you take Legendre symbol a times b modulo p, then you can decompose this into separately Legendre symbol of a modulo p and Legendre symbol b modulo p. And here I write down exactly equal, not congruent, just equal. The third property right here, if you take Legendre symbol of any square number modulo p, then this is always equal to 1. The third property immediately applies that therefore Legendre symbol of 1 modulo p is just 1. However, let's try to figure out what Legendre symbol of -1 modulo p is. And in fact, it splits into two possible cases. So this will be equal to 1 if my prime is congruent to 1 modulo 4. If otherwise, so p is congruent to 3 modulo 4, then this symbol equals -1. So this result solely depends on what prime number we choose. Now let's quickly prove those 5 properties. So we start from the first one. We take two elements, a, b. Those are congruent modulo p. I always forget to write this bracket. Therefore, it implies that a raised to the power of p minus 1 over 2 is congruent to b raised to the power of p minus 1 over 2, and again in the world of modulo p. However, notice that each of those elements, so in particularly a to the power of p minus 1 over 2, is actually congruent to this Legendre symbol by Euler's criterion. Likewise, b raised to the power of p minus 1 over 2 is congruent to Legendre symbol of b by those preceding results. So in fact, we get that Legendre symbol of a modulo p is congruent to Legendre symbol of b modulo p by modulo p. So we get only AP is congruent but not equal. But we need to check that those are in fact equal. Let's just subtract both sides by this Legendre symbol, and we get that this thing, this difference, is congruent to 0 modulo p. So therefore it means that this object can be equal to either 0 or p or 2p or even -p, and so on and so forth. However, notice that Legendre symbol produces 3 possible outputs, either 0 or 1 or -1. So the smallest number that might be possible here is -2. The biggest, on the other hand, is +2. So it means that this element cannot be p, cannot be 2p, and cannot be -p because p is an odd prime. So the only possibility here is when this difference is going to be equal to 0. And thus, this follows that those Legendre symbols are equal. The second property is actually even easier to prove, so I think I'm entitled not to explain this in detail. However, again, we get only that this Legendre symbol minus the product, this Legendre symbol and this one, is actually not equal to 0 but only congruent to 0 modulo p. But you can prove with the same manner as we did previously that this difference can only be equal to 0, and thus this means that this Legendre symbol equals the product of those Legendre symbols. Something like that. The third property, sorry, but this is really immediate one, because a squared, this element is always going to be a quadratic residue modulo p, so therefore this Legendre symbol will always produces you just 1. And as I mentioned before, this one comes from the third property. In order to show this, we again have to apply Euler's criterion. So Legendre symbol of -1 mod p is in fact congruent to -1 raised to the power of p minus 1 over 2, and the whole thing is modulo p. And this time, what result will be here depends on chosen p. And let's try to investigate this in detail. If p turns out to be congruent to 1 modulo 4, then by definition of mod, you can write this as p minus 1, which is equal to 4 times some other multiple k. So therefore, this prime is actually 4k plus 1. But if you try to plug this p into this fraction, you will get that this is actually 2k. But this number is in fact always even number. So you just take -1 and raise to the even power. -1 to the even power will be just +1. And thus, this Legendre symbol, -1 modulo p, is going to be here first of all congruent to 1, but you can prove similarly that this is just equal to. The last possible case is when p is congruent to 3 modulo 4. Then likewise, you can express this as prime number, which is 4k plus 3. Plugging this p into this fraction, this gives you a number 2k minus 1, which is the example of an odd number. But -1 raised to the power of this odd power gives you just -1. So thus, this Legendre symbol must be just equal to -1. Recall that p congruent to 2 modulo 4 is actually not possible, especially when p is odd. Now here's how we can apply those properties. So there is the question, is there a solution to the following equation: x squared is congruent to 12 modulo 23? And if you recall the definition of quadratic residue, this question is equivalent to asking whether 12 is going to be a quadratic residue modulo 23. But this is equivalent to asking ourselves whether 12 mod 23, whether this Legendre symbol is going to be equal to 1. So that's what we need to answer. Take a look at this chain of equations. So first of all, you take Legendre symbol 12 mod 23. Notice that 12 is just 4 times 3. And then you apply the second property where you can split this into two separate Legendre symbols. 4 mod 23 and 3 mod 23. Now 4 is just 2 squared, so you get Legendre symbol of 2 squared mod 23 and Legendre symbol of 3 mod 23. And you know by third property, this is just 1. So you are only left with the following Legendre symbol 3 mod 23. But this in fact can be written as congruent to 3 raised to the power of 23 minus 1 over 2 by Euler's criterion, which is in fact 3 raised to the power of 11, and I think you are capable of finding out what is congruent to, so I'm just leave the answer. This is in fact indeed congruent to 1 modulo 23. So therefore we get that this Legendre symbol is in fact 1, is indeed 1, and therefore there is a solution to this equation. Here's one fascinating corollary that can be explained without writing a proof. That is, if you sum up all Legendre symbols where you run here from 1 to p minus 1, you get that this is equal to 0. Let's recall that Legendre symbol means we answered the question whether this element is a quadratic residue modulo p. Now recall the result from the previous lecture. As long as p is an odd prime number, then we have p minus 1 over 2. The first half of elements are quadratic residues, whereas the last half of elements are quadratic non-residues modulo p. So therefore, this sum contains half of those elements are going to be plus 1 and half of those are going to be negative 1. So this totally gives you just 0. And finally, here's the bonus result that worth mentioning. So we know in number theory there are infinitely many primes, just primes. But we do not know whether there are infinitely many primes of the form when p is congruent to 1 modulo 4. And in fact, there are infinitely many of them. The result will be proven by contradiction. We're gonna suppose there are not infinitely many primes, and we just enumerate all of them, p1, p2 up to pk. So there are only k possible primes such that all of them are congruent to 1 modulo 4. The first prime here is 5, the second is 13, and so on and so forth. We're gonna construct the following number, capital N, which is just the product of all primes p1, pk, multiply the whole thing by 2, whole thing squared, and then we just add 1. Because those elements are the only possible primes, n is clearly bigger than all of those, so this number cannot be prime, thus it's composite, and since this element is odd, as you probably can see from the construction, then there is an odd prime number p such that it divides this n. And please keep in mind that this p can not necessarily belong to the set of those primes such that are congruent to 1 modulo 4. It might be a prime such that it's congruent to 3 modulo 4. We still have no idea, but we will see right now. So this just implies that this capital N is congruent to 0 modulo p. Knowing what n is, we can rewrite this as the following. 2p1 times pk, and the whole thing squared is going to be negative 1 modulo p, right? So this is just a number, let's call it x. Squared is congruent to negative 1 modulo p. So it means that we have the solution for the following equation, and this means that negative 1 is going to be a quadratic residue modulo p. So it means, in the language of French bad boy Legendre, it means that this Legendre symbol -1 mod p is in fact equal to 1. Okay, but what do we know about this Legendre symbol? From property 5, this is going to be equal to 1 as long as this prime p is congruent to 1 modulo 4. So in fact, this prime, this one, belongs to the family of those primes. So this p must be one of those. So therefore this p has to be equal to one of those pi's over there. So therefore this pi, this divides our capital N, which is exactly this squared plus 1. However, we actually also know that this pi divides this element. So these two imply that actually pi divides 1. It means that this pi has to be equal to 1. But pi is just a prime number, but this is a contradiction. 1 cannot be a prime. And we finished the proof right here. Now, I really encourage you to practice on computing Legendre symbol, and that is, I would like you to compute Legendre symbol of 18 modulo 43 and Legendre symbol of -72 modulo 131.